Okay, so I think we'll start the second half of the talk now. In terms of the second half of this talk, we're going to get quite technical. I want to at least expose you to all of the kind of new features that are coming out in TensorFlow, because in my experience, it's very important to stay up to date. Things move quickly. This is kind of the state of the art. And it's important to understand what is available so that you're not re-implementing things that are already coded for you and likely coded more efficiently than you would code just by hand. Tomorrow, we will go kind of in the opposite direction of theory, more on the theory, also backgrounds into like floating point operation counts and some of the computational aspects. But in particular, we'll go through all of the underlying principles behind dense layers, convolutional layers, and also mention why we're using neural networks in the first place. So we'll kind of have more of a theoretical discussion tomorrow. Today, we're going to wrap up with some of the more technical and in-depth ideas behind TensorFlow. So hopefully, the first half of this talk gave you somewhat of an introduction to the general ideas, the core concepts behind TensorFlow, and now we want to move on to how to actually write kind of the code in a structured way, which will save things and monitor things for us automatically, so that we're not always writing the same code. And the first concept that comes up in this framework is that of a monitored session. So these are effectively the same as a tf.session that we were using before. They are used to execute our graph or operations on our graph. The difference is that they are basically offer streamlined ways to initialize variables, use hooks for basically situational decision making. The idea behind hooks, one of the ways I think of it is it's basically a replacement for you sitting at your computer waiting for something to happen, waiting for the loss to get too low or not a number to come up. You can specify you can tell the monitored session to do something in the event that something happens like that. And then also session recovery after errors are raised. And I find this in particular useful for training on, say, the compute clusters that we have here, or when you're working over like SSH. If you're working on an external computer, it's, if your connection gets interrupted or if something happens on the computer, you can always recover in a pretty much seamless way. There's really not much that you have to do, as we'll see. And in addition to the monitor session, we have a monitored training session, which basically is just a slightly larger wrapper, and it helps automate the process of saving your checkpoints, creating summaries, and is also useful for distributed computing. You can kind of assign these chief and non-chief workers, which is a little beyond the scope of today's talk, but it's just something to know. There are definitely a lot of things beyond this which are facilitated by the use of these monitored sessions. So as I mentioned, hooks are basically ways to automate decisions during the training process. So things like checkpoint saver. So if it's been 500 steps, save a checkpoint. Stop at step hook, maybe determine how many iterations you want to go through. Not a number tensor hook. So if a tensor returns a value which is not a number, maybe you want to stop training, or maybe you want to restore from the previous checkpoint and try again. Maybe you want to do something in that case, and this allows you to basically, press train, press go, and maybe go to sleep. And when you wake up, you won't just have a string of not a numbers, and you wasted all of that time, right? So this unfortunately happens a lot, but these are very convenient. So I would recommend looking into these. They're a little bit abstract, but they're worth using, in my opinion. In these monitor sessions, one additional kind of aspect of the graph that you need to create is a global step tensor. So this is just basically, instead of manually saying, okay, step starts at 0, and then step is add 1 every time I loop, we're going to define a tensor in the graph. And this is actually a dual purpose, and there's some reasons why you would want to do this anyway. But in any event, it's necessary to define this global step, basically a tensor in the graph which tracks the current step of the training process in order to run these monitored sessions. And the step will automatically be incremented by passing the global step to the minimize method of your optimizer. So here we have minimize. Self.loss is what we're going to minimize. So the self just means we're working in this class setting now, so I'm going to start using that more often. And the global step is just going to be self.step. And every time this optimization step is called, it will increment the step. It will be step equals step plus 1. But the benefit of this is that if you're testing or if you're not optimizing, it won't increment that. So it kind of only increments it if you have, in fact, performed an optimization step. To use the monitored training session, we replace the somewhat easier with tf.session as sesh with this more verbose but configurable block. So we have this train monitored training session. We specify a checkpoint directory, so we tell it where we want to save basically our model. Remember, the variables and the graph will be saved there, and we can restore the full model, the trained model, at different steps, basically. And we also typically give it a hook with a stop at step hook. So this is the maximum number of training steps. So we tell it the last step. Once the global step gets up to 1,000 in this case, we'll stop training. And this will be in our training loop. We'll use this basically information to define a while loop, as we'll see in a second. And then we can just specify how many checkpoints that we save, or how often rather we save those. In this case, every 100 steps. And there's a lot more options. Again, the API is probably a good thing to consult. If you just go TensorFlow and you type in monitored training session, you'll see a more detailed list. That being said, it's not always the most helpful. So I'll try to walk through some of the parts that are not really explained in full detail. One important thing to do is to pass the session to the model, and we'll see why this is important later. But in this case, we can first initialize a model, and we'll give it some flags, which we'll cover just in a few slides. So we'll give it some parameters, basically. We'll initialize that. We'll build the graph, build the model, and then we'll start this session. And once the session is started, we'll set or specify this training session as the current session. And so what we'll use this for basically is we'll have a separate training session, and then we'll have afterwards a validation, or rather a evaluation session, which is just going to be a standard tf.sesh. And then we can train after that. But this is kind of the workflow. Again, it's just slightly different. We first initialize our instance of the class. We then set up a training session, and we pass that session to the graph. As I mentioned before, we have this hook that tells us we need to stop after a certain number of steps. And the way that we use that, we actually use that as a cue to stop, is that we iterate not using for n and range 0 to 1,000 or something. It's kind of a little more natural. We say, while we should not stop, basically. While not, self-sesh should stop. So the session will be passed a request stop call, and its attribute should stop, or this method, I guess, will return true, basically, if it should stop. So this basically tells us, keep going through until the session has received a kill signal, basically. And this is helpful if you're using multiple hooks, if you have multiple different kind of cues for stopping training, for just summarizing that into one kind of convenient loop. And so then you just update your global step, if you're going to use it. And so you may use this, for instance, to only display your progress every 10 steps just for feedback purposes, or only to test like a validation set every 100 examples. So you may want to know what the step is. But if you're not using that, it will be automatically handled in the background. So the model set session, as I mentioned earlier, is really just a switch between using the monitored training session and then using it after training. Because the monitored training session is somewhat fixed, after you've hit that last step, it will throw an error if you try to run anything again. It will say should stop, or a request stop has already been requested, and you've tried to run another operation. So once you finish training, once it ends, you can just open a vanilla session or a standard session, just as we did in the previous set of slides, and then set the session now, or reset the session as this new non-monitored session, and evaluate it using the method as we discussed earlier. Another thing that's commonly used is learning rate. And so one way that you can do this is using a feed dictionary or placeholder and slowly increment it down using exponential decay. The issue with this, and this is something to keep in mind, is that that placeholder, or the value, the current value of that, is not a TensorFlow variable. It's just a Python variable if you're just feeding it in, and it won't be saved with the model. So the saving process only concerns variables and the graph. So if you're constantly feeding in a decaying value for the learning rate, and say it gets to 0.001, but you started at 0.1, when you restart that model, if you want to continue training, it will go back or revert to 0.1. But the workaround, since it's so natural to use, is just to define the learning rate in terms of an exponential decay. You give it the initial value and the step, the global step, and from those values, from these arguments, it can always recover what the current learning rate is. So this will be saved and executable, or retrievable rather, when we restore from one of those checkpoints. So this is preferable to just feeding the learning rate and manually adjusting it. And then one just technical note, depending on how you set up your model, this may be a bug of some sort, but it often throws an error if you try to save a summary without providing a feed dictionary for, say, like training is the only one I think I use. And it throws an error for some reason. So I found you can avoid this by just setting the save summaries to none and just doing it manually. So just a technical point that I thought I'd put out. So going back to some more kind of usability features and some convenience, convenient ways to kind of organize your code, and also basically a way to follow the TensorFlow code. If you go through the source code, you'll see this a lot. Is to store command line options or different hyperparameters in the form of flags. And so if you go through the TensorFlow documentation, you'll see all over there's FLAGS in all caps, flags, dot this, dot that. And what those are basically options that you have. And you can specify them from the command line using these double dash and then the name, like batch size, for instance, and set it equal to, say, 64. And you can also have like a toggle, like use the GPU, because we have it available now, but if I'm running it at home, maybe I won't have it available. So we want to have the option to basically do this without having to go into the code and kind of changing things every time we run it on a different computer. So Python has a module argparse explicitly designed for this. It's very easy to use. You just create a parser. You give it a description, and then you add arguments to it by defining what that name of that argument is. And then optionally, you can give it a default value and the type of information that you're giving it, and then a help description. And so this allows you to write code that's more usable. You can actually type, Python model.py help, and then it will display all of these number of training steps, training batch size descriptions, so that you know what options are available and what they refer to. Once you define this, so I defined it as flags, I've parsed these arguments. So it basically retrieves any information from the command line, and it stores them in roughly a dictionary. So you can access these by just flags.batch size, for instance. You can also unpack the flags, which is typically convenient. So in the previous a few slides back, I just said, I want to create an instance of a model, and I don't want to pass it every option one by one. I'll just say flags, all caps flags. So what I can do, instead of just going through and writing one of these for every option, self.batchSize is the flags.batchSize, we can just write a small loop going through the keys and values of the dictionary, the internal dictionary of this flags object. And so if you just run this, then it will automate the process of manually just writing these out. So I think it's quite helpful, especially if you want to kind of add arguments and take away arguments. As you're rewriting the code, you don't have to always make sure that the arguments match up. It's just a much cleaner way of writing. And then you can initialize your model or create an instance of your model by just passing those flags to the object constructor. One note when we were doing this, so I had mentioned use GPU in the one of the slides, and that would you would think maybe you could just put use GPU and then true and false to provide it a value, but unfortunately the command line options are going to be interpreted as basically strings. So if I put use GPU false, if I append that to my Python call, it will produce a value which is the string false. And you can work with this and fix it, but strictly speaking, the word false is not 0 and it's not false, the Boolean value in Python. So you could add another line to process this, but it's just as easy to define this instead as a basically a Boolean flag that either is on or off. So it's kind of a toggle. So in this case, I've set the default as false. So if you do not see this flag, it will be false. And if this flag comes up, then store a true value, store the Boolean true. And this will work as expected. So use GPU indicates that that option will be set, and leaving it out, it will keep it false. So obviously, that doesn't actually enable you to just use the GPU directly. You have to actually configure it. So I just thought I'd mention this, although there's going to be more reading that you have to do to get this installed all the way. But you can see these 2 pages here at the top in the API outline the general idea. And basically, you need to install the CUDA toolkit. And I only know how to do this on Linux, but I'm sure it's similar in other operating systems. You set the LD library path and append basically the CUDA 9.0 library file. And then you also need to install the deep neural network libraries. So these are like optimized implementations of some of the core aspects of deep learning on GPUs, and install the GPU version of TensorFlow also. So a mistake not to make. But it's also available just as before, it just has GPU appended. One other thing is that you can specify which GPU to use by using CUDA visible devices, the environment variable, equal to 0 is your first one, 1 is your second one, et cetera. So it starts at 0. And there are other options that you can pass. So it's slightly different than just running it on CPU, but relatively manageable. And you can let me know if you have any questions on that. In addition to the setting up the GPU basically on the system, you have to tell your code in order to kind of configure things correctly. You want to tell your code how many GPUs are available. And it generally will figure this out correctly, but just to be explicit here, for instance, if we wanted to use the GPU flag that I mentioned before, we define a configuration for our monitored session which either specifies 1 GPU is available or no GPUs are available, depending on whether we are using GPUs or not using GPUs. And also, if you're using a GPU, you can set this allow growth option so that it starts out with basically a small amount of memory and grows to consume as much memory as is needed during runtime, instead of just allocating that at the start. So allow growth starts out small. It may just grow anyway, but it's one option that you may want to look into the descriptions a little bit more in the API documentation. And then also just one more thing I want to put, by default, they save 10 checkpoints. If you're interested in customizing some of these options more, there's a scaffold, the concept of a scaffold where you can have a little bit more fine-tuned control over how your session will run and some of these automated processes work. So here I'm just telling it to save, but only save 3 of them and delete any ones that are further back. And speaking of saving, we want to know how to actually use these. So I've mentioned them a few times now. So how do we actually get the checkpoints back into, say, Python, for instance, if you want to resume training? So if you want to do this by hand, you initialize a new saver. So TF train saver, it's used for saving and restoring. So you start out with a blank saver, and then use the restore method directed towards the latest checkpoint. So you tell it where are the, what directory are the checkpoints in, and this tf.train latest checkpoint basically just reads a file, the checkpoint file, which lists the current checkpoint. So it'll get that, kind of automates it for you, but still a little bit cumbersome. And then you can set that session and evaluate, for instance, for evaluation after you're done training. But monitored training sessions will do this all for you, so it's somewhat nice. You just tell it where the checkpoint directory is, and it will automatically check at the beginning before it starts training to see if there are checkpoints to restore from. It's very convenient, but it's also somewhat subtle, so you have to keep in mind that this is happening. If you go in and you change the size of your network or some parameters and don't remember to delete those checkpoints, it will attempt to restore from the original checkpoint, and the sizes won't match, and it will throw an error. So it's a very common, but the reason is you have to keep in mind it's always trying to restore, so you need to clear that checkpoint if you're changing fundamental aspects of the model, things like the network size. And you'll see something like this with much more. The error messages are quite verbose, but this is the key aspect. The assign requires shapes of both tensors to match. So this would be what happens if I change the dimension of one of my layers. So one interesting aspect of these frozen models, or these checkpoints rather, is that they can be converted into what are referred to as frozen models, and they're saved in these protocol buffer formats, which are lightweight and language neutral or language independent. And you can read them. There are string versions, but they're also usually written in terms of bytes. But these are just effectively just very short descriptions of all of the necessary aspects of your model. Again, the graph is saved, and the weights and their values are saved. And from that information, you can reconstruct the model in different languages or on different platforms, and basically, it's just kind of a nice, simple way to make portable code. So if you're interested in learning more, you can look at this website. It's just the TensorFlow's, or Google rather's, protocol buffer format. And it's basically used for deployment. If we want this on multiple devices, we want something that's basically just what we need and no additional instructions. Related to that is frozen models. So when we're thinking about our model, the training process has a lot of basically extra things added to it, and especially the Python code for it. What we need is really just the single, basically, ability to make a prediction. So we just need the graph and those weights. And we may not even need the full graph. So again, I won't go through the kind of somewhat gory details of this, but we can specify basically a specific thing that we are looking to access. In this case, it will be the tensor prediction. And we can save the necessary components in a protocol buffer file, in this case named frozen model. Okay, so you can kind of go through this, and once you save that in the protocol buffer format, and you know what your input and outputs are, so I want to go from X and create a prediction, you can prune or optimize your graph so that it only keeps what is actually needed. So if you had all of this complex training processes and you only want to now make a prediction, you may be able to get rid of a large portion of the graph. And this optimized for inference library imported at the top here allows you to do just that. So they're a little long-winded in how you use them, but again, I'll put these slides up and you really can just use this, replacing your input node list, output node list, and the folders that you chose to work with. So in this case, I've used checkpoints. So that's nice. How do you access these? Again, it's a little bit long-winded, but hopefully you can take some time after if you're interested in working with these, for instance, for putting them on mobile devices. Basically, you get the graph, you load the graph, you find the tensors by name. So again, remember the :0 format. I've added prefix here for compatibility with older versions. And then we open a session and basically can just run that prediction. We have that session available now. So we can do this. For instance, in my case, I usually freeze my models once they're fully done, and then I go through and evaluate it on the whole data set. If you're working with like 1 million data points, it's worthwhile to freeze the model first and then run through in the optimized version. So you can save some time by doing this. Okay, and as we mentioned near the end of the first half of this talk, one of the key properties of TensorFlow is that it's scalable, but up until now, we still have been just loading everything into RAM, and there are some kind of slow kind of bottlenecks that can be caused by these input pipelines. So the TF record file format aims to basically circumnavigate the Python interface. It's trying to just basically pass the data to where it needs to be. And it works very efficiently. It's very scalable. It's very easy to use once you define the file. But the files themselves are somewhat complicated, I think, the first time you see them. So I wanted to try to break this down a little bit. What you typically have when you think of an example is a collection of arrays, maybe a string or maybe a label. But in some sense, it's an array or it's some data type in NumPy or just in Python in general. And what you want to do in order to create an example, that will be usable in this TF record format, is to first create a feature of a specified type. So for instance, we may have a bytes feature for something like an unsigned integer or for like image arrays, or we may have a float feature for something like a regression problem where we're trying to get a precise decimal point value. We combine all of these features into the aptly named features format and then pass the features into an example. Okay, so that's the workflow. So in order to do that in the code, there's a few things that TensorFlow provides us, and we just need to kind of string them together in the right fashion using the diagram from the previous slide. So we first want to import the feature, float list, and bytes list functions from TensorFlow.train. And we define this internal feature or internal function bytes feature to process basically a NumPy array of values into this feature. So this will return a feature which has a bytes list. So the bytes list is then converted to a feature. And we may also have float type values. So we first, in order to get this to work, need to basically flatten the array and then treat it as a list of floats by basically just forcing it to have every entry as a float. So this is the way that I've been able to get this to work. It is very scarce in terms of documentation, so I thought I would at least show you how to do the two most common examples. So typically a bytes list would be used for like small unsigned integers, and float list obviously for floats. And now, once we have these features, so if I go to this slide, we can combine the features. Okay, and so this is where I'm going to call the bytes feature or the floats feature. So I've just kind of commented out the float version and the bytes version is highlighted. So the flatten as type numpy uint 8. So we just want to flatten this. It's going to be a list. We're going to treat it as a list. We're going to forget the structure, and we'll tell it the structure later. And we convert that into a feature using that internal function and pass it into a dictionary, which has a label that we'll use to call it. So maybe it's just called data. And that is used to create the features, so this TF train features, of an example. So it's somewhat of a windy process. But again, we're really just following that first diagram. You just pack these things together. And once you have the example kind of in that correct format, we can write it to a file using this serialized to string and writer.write, where the writer is just from the TF Python input-output module. And it will have the file name training.tfrecords. So quite a bit goes into it. Once we have that, we still need to basically reconstruct that data. So as I mentioned, we have flattened the data basically for storage purposes. But now we need to recover any structure that was there. So for instance, if we had some 28 by 28 images, what we're going to do is we're going to load these in. We're going to parse the data, kind of get it back into the shape it was originally in by telling TensorFlow what that resolution of that shape was. So it has a list. It unpacked, or it vectorized or flattened it in a certain fashion, and it knows exactly how to basically repack that so as to get the original data back. And we basically get a function here, this parse single example, to get the example protocol buffer format, or a single example, as a template to use to read the data afterwards. So once we get this parsed data and we access the dictionary, remember we had the dictionary of features, and we labeled one as data here, then we can recover those and then decode them because they were bytes. If it wasn't bytes, then you could just access it directly because it's going to be in a floats already. So somewhat complicated. And I'm sure you'll kind of have to go through this on your own to really understand it. But once you have that written, so all of that was to define this TF records format. And this is the recommended format. If you watch the developers summit, they all kind of encourage you. They always kind of highlight or hint at, it's best to use this TF records format. It is somewhat of a challenge to get started with, but once you write it for one application, it's really just a copy and paste, maybe switch some sizes around. So I would say, don't get thrown off by all of the steps that we've just gone through. At the end of the day, we just need to be able to make these TF records files, and then we can greatly increase the speed with which we process data. So a lot of times when we're working on kind of smaller desktops, the input pipeline is a large bottleneck, and we don't want that to be the case, especially when working with large data sets. So once we have the TF records format, files saved in a TF records format, we have a lot of kind of optimized, efficient algorithms to work with. And in the single file example, I just defined one TF records file, but we could also imagine maybe every 10,000 examples defining a new file, and you can even distribute that across a network if you need to. And the TensorFlow has a kind of convenient way of retrieving all of those files. If you just put an asterisk in the position, if you named it like training 1, training 2, for example, it will unpack that using the list files function. And to do this, and again, this is basically taken directly from the TensorFlow Developers Summit this year. To do this in an efficient fashion, what you can do is assign a fixed buffer size for each of these files. So we're trying not to load everything into memory now. We're trying to do this in a kind of smarter, more scalable approach. And we can define, in this case, just 4 megabytes. I just basically adjusted it for my data set, and return a TF record data set. So this is basically the equivalent of the from tensor slices, except the optimized version, which reads in a file name that will pass it from the list of files with a specified buffer size. And so this files.apply, so we're going to take that files list and we're going to apply the parallel interleave with the TF record dataset function defined here applied to those files. Okay, and this parallel interleave basically reads from multiple files at the same time, especially if you have a network, maybe there's one that's falling behind, and whichever are available, it will put into position interleaving, kind of, I guess, combining them kind of one by one. Maybe I should show a diagram at the end, but they're interleaved in the sense that maybe dataset 1 goes here, and then dataset 2, dataset 3, dataset 4, dataset 1 again, dataset 2, where the cycle length is defined right here. In this case, it's 8. And again, this is something that you probably will want to go through the API in more detail, but I want to at least give you the skeleton so that you know what you're looking for. And this is the basically the recommended approach for defining these TF records data sets and reading from them efficiently. Once you have done that, we're basically back to the position in the first half of this talk where we had created a data set from tensor slices. Now we want to batch, shuffle, repeat, maybe transform our data set examples in some fashion. And to do this quickly, we don't want to just compose functions. We don't want to just, okay, let's first shuffle it, then let's batch it, and then let's apply a transformation. We want to do this in a more clever fashion, which takes advantage of the fact that we have this data available. We have this, we're working with this to batch it. We may as well apply a transformation at the same time, for instance. And this is accomplished or provided to us in TensorFlow in the form of fused operations. So a fused operation does exactly as I mentioned, operations basically in parallel to some degree. It's a better or a more efficient way of applying these in series. So TF contrib data map and batch, as you would expect, will map or apply a function. In this case, that parse data function. So it's going to reformat, restructure our examples, and at the same time, batch our data into groups of 100 or whatever our batches happen to be. And we can do this also. We have a number of parallel batches and different other arguments as well that you can look up in the API. And, oh, I missed at the top, there's also shuffle and repeat. So you can do the shuffling and the repeating in a fused way as well. So these are two kind of the standard, typical example. You shuffle and repeat, and then map and batch, where the mapping aspect refers to basically unpacking your data. And then this prefetch is just to basically how many examples or batches in this case you want to get beforehand so that you're ready for the next iteration of training. And then you define your iterator, again, just as before, just make one-shot iterator. Okay, once you have the training data set defined, you can do the exact same process to define a validation data set. And in general, you may have multiple different data sets for different purposes. And we want to define a code which can accept different data sets. We want an easy way to switch between the data sets. And we can do this using data set handles, which are basically just a string, kind of has some technical details at the beginning, but then it just ends with the name of the data set that you're using. So the string handle is basically just a label which tells TensorFlow where to go to get the data set. And what we can do is define our graph, instead of putting the iterator in there directly, define the graph with an iterator which first looks up what data set it's working with. So this is referred to as a feedable iterator. And we can use this by defining a placeholder for the dataset handle. So what's the label? What's the name? Is it training or validation, typically? And passing that data handle to the from string handle method of the iterator, or tfdata.iterator. Okay, so this will say, for instance, this might be something along the lines of training, and it'll say, okay, we're going to the training data set, and we want to get the next batch. So that iterator.getNext will get the next batch, and we'll make a prediction from that data, the next batch. But maybe the next step, we want to apply this to a validation data set. So we'll instead feed validation, but none of the remaining code has to change. Everything is still the same. The data is now coming from an iterator, which is reading from the validation set. So it's kind of redirected. But this avoids us having to actually pass the arrays or the data concretely. We just pass the handle, a string, to where the data set is in the graph, and the feedable iterator can take that and produce the next element or batch of examples from that data set, the target data set. So as I mentioned, typical application, training, and validation. So you may define a feed dictionary with training and the dataset handle. So the train dataset handle, training is true. Use that as a feed dictionary. Now if you want to validate, you just set training to false and give it the validation dataset handle. And maybe write a validation summary as well. In terms of summaries for using a different data set, you typically just do this by hand, but it's not too hard. We just define one writer for the training set and one writer for the validation set, and we can put those in subdirectories of the logs folder or whatever directory you placed it in, and those subdirectory names will be used as the labels on the TensorBoard visualization. So for example, using the code that I just showed, we can see the training loss in orange and the validation loss in blue. And we see from this graph there's some overfitting. When we're working with a training set, we're somehow below the validation set. We'll go into this in more detail, but it's nice to have this as a diagnostic tool so that you can interpret and understand what is going wrong or what is working well with your network, and make sure you're not falling into categories such as poor generalization. It's kind of fit to what you've seen, but it doesn't generalize to those examples which you have not seen yet. And another common example of when these TensorBoard summaries are helpful is in terms of things like early stopping. So in this case, we see, once we plot it, that the model actually was very accurate. I mean, here, or even at this dot point here, we've seemingly reached our kind of optimal performance, at least for these hyperparameters. It may be worth tuning again. But what can happen is the gradients or the training procedure can somewhat explode on itself. It's been working so hard and it hasn't been seeing any improvement, and then it makes some kind of crazy step in the wrong direction, and that just kind of builds and builds until you really lose accuracy. And in this case, it comes back down, but in some cases, you can shoot up and get things like not a number. And in any case, you don't want to have your network performing worse at the end of training than it was at an earlier part. So this motivates the idea of early stopping, which basically is the concept that maybe I have a threshold. Maybe if my loss is below 0.001, then I'm OK with that. I don't need it to be more accurate for my particular application. I can stop training whenever that is reached. And one way to do this is with a custom hook. And I will briefly go over this because this is really getting technical at this point. But I think it's worth noting that this is really kind of the level that you can really control everything about TensorFlow if you understand kind of these hooks, these training sessions, the layers module. We've really covered almost everything that I use in my own research. And what we're about to go through is a little bit complex, but I think it's still manageable. So what I'll walk us through is the idea of how to create your own hook, a custom hook, which basically manages your own control flow. And the basic ideas are provided by the session run hook, which has a begin, a before run, and an after run method, which are called, as you would expect, kind of at the beginning. So as soon as you start the training, so maybe you say, OK, get the global step because I'm going to need that, and initialize my parameters for this hook. And then before run is called right before you make a session.run call. This will be used to specify what operations you want to be evaluated. In addition to what's being evaluated directly, maybe you need to know what the loss is. So I directly need the loss because I want to check, am I below that threshold? So you tell it in before run, please evaluate the loss and possibly provide it an extra feed dictionary if necessary. And after run, you can retrieve the values from those requests, those fetches that you've included, and make a decision on what to do. For example, request stop if you're below a certain threshold. And just in terms of the API, it's hard to find on the actual API, but on the source code buried in there, there's actually a relatively good explanation. So if you go to the GitHub page for the source code for session run hook, it has a little explanation, and in particular, there's a few other methods that are called. We see it first calls the hooks begin, then creates the session. There's also an after create session, and then while the stop is not requested, it will keep calling the before run, trying to get the results, possibly catching an error, and then run after run. And then there's end, and then the session is closed. So this is kind of the schematic, but we're getting down to really the deep implementation details of TensorFlow at this point. And we can relatively easily define this hook to do whatever we want. So I just gave an example here of an early stopping hook, which is not implemented in TensorFlow, not at least as of the writing of these slides. And what we want to do is basically import a base model. So our session run hook, we want to get that as a template, and session run args will be used to basically pass the arguments to the session, the requests for arguments. So I'm going to define a class. It'll be an early stopping hook. It will have a few methods. First, the init. So maybe I'll give it the loss name. What is the loss that I want to check? What values, if any, do I need to feed into the graph in order to compute that loss? What is the tolerance that I'm willing to accept? And when is, or how often, so I've just kind of made these names up, but how often should I check for early stopping? Because I don't want to do it every step, since that would be very, very slow. Yeah. After we've initialized the hook, we want something to happen at the beginning when we call the session. And what typically this corresponds to is maybe setting an internal step and retrieving the global step from the graph. So I'm going to get the get global step from tf_train to know what step I'm at in the training process. So I'll use that just as a measure of how often I want to check for early stopping. And once we have that, I guess on this previous slide, we'll be able to get other tensors as well, in particular the loss. So in this case, the global step has its separate, a separate function for retrieving it. But in general, you first need to get the graph by using the run context session graph. And then from within the graph, you need to get the tensor by accessing, using the method getTensorByName of that graph. So just a note. So global step is easy to get because there's a predefined method. Other tensors can also be retrieved by name, though. So in particular, we'll use that in our before run. So we want to initialize. We want to tell it, what are we going to do during this run call? I want to add on a few operations. And what I basically tell it to do is, if we're at a stopping step, maybe every 1,000 steps, for instance, I want to get the graph again, and then get the loss tensor, because that's what I'm working with. So I'll get that by name. I've already assigned the loss name. And I'll define, if necessary, a feed dictionary. So this will just basically, again, similar to unpacking the flags for a model, go through and set the placeholders, or retrieve the placeholder tensors, and populate the dictionary. So it's just a little technical, not always needed, but in some cases it is. And then we use the session run args, again, to basically specify what we want to add on, what we want to fetch. And in this case, we want the global step and the loss. and we've given them names in this dictionary as step and loss. And if we're not at that stopping step, we just return the step. Okay, so that's kind of the most technical part. After that, or after the run rather, we just retrieve those values in the form of a dictionary. So the run values will be passed. So this is the format inherited from the session run hook class. And it will always be passed the run context as well as the run values. And that run values will be a dictionary containing the values that you requested with the key corresponding to the label you provided it. So in this case, the step and the loss were the keys. And what I'm going to check here after each run, after each time the stopping step has come at least, is whether or not this current loss from this run is less than the tolerance that I've specified. And if that's the case, I just tell the run context, basically the sessions, our way of accessing the session, to stop. I request a stop. And then that loop that we had inside, while not should stop, will break and will end because we've achieved our tolerance. One way of doing this without a feed dictionary, so you can use a feed dictionary and that implementation will work with it, but one way to do it without a feed dictionary is to just define a separate early stopping loss. So in this case, I've taken the validation and I'm going to batch it into size of 20,000. So typically when you check for early stopping, you want to take a very large number of your validation set and see if it's performing well, basically on the whole set, if that's possible, if you can fit that into memory. So I go through the exact same procedure as before for creating the data set, and I just compute a separate loss. So this way, I don't need to use a feed dictionary, but you can also use the feed dictionary, and it should be possible to use that with a data string handle as well. Once you've defined that, all you have to do is add it, just like we did with the stop at step hook. You just provide it to the list of hooks, maybe set your stopping step and your stopping tolerance, and that's effectively it. So we've gotten through all of the very, very technical details, and hopefully I haven't lost you too much. Tomorrow we're going to go into the neural network sides, the theory, and then on Wednesday we'll combine this so that we kind of have an idea of how to create kind of deeper models and work with some of the generative and the auto-encoding models that have kind of sparked kind of resurgence in neural networks, feed-forward networks in particular. And then I just want to point out, again, there's a GitHub. There's some more examples in the models folder, some full, complete working examples, which we'll also discuss a little bit on Wednesday, and some brief explanations on the web page. So I appreciate you all taking the time to come out today, and we will meet again tomorrow from 3 to 5 as well. If you have any questions, please let me know, and I'll also be available after.